Hello, welcome to an A-level AQA physics video. Today we'll be looking at 3.2 particles and radiation. We will look at the subtopic 3.2.1.2 stable and unstable nuclei. So to begin with, what causes a nucleus to decay? A nucleus decays if it is unstable, meaning the attractive forces keeping the nucleons together are weaker than the repulsive forces pushing the nucleons apart. Note, nucleons refer to either protons or neutrons, which are found in the nucleus. A different way to think about decay is that the unstable nucleus has too much energy and needs to lose some of that energy. This can either happen by weakening the repulsive forces or strengthening the attractive forces, leading to a decay. This will mean some particles and/or some energy will be ejected from the nucleus, leaving behind a different, more stable nucleus. The main forces acting inside a nucleus are the electromagnetic force and the strong nuclear force. Note, because some nucleons are very light, the gravitational force can be considered negligible, although the gravitational force does exist between any object of mass. Now, the electromagnetic force acts between just protons, and because they have a like charge, they repel each other. So in the nucleus, the electromagnetic force is always repulsive. Note that neutrons do not feel an electromagnetic force because neutrons have no charge. The other main force is the strong nuclear force. This force acts between all nucleons, so it can act between neutrons and neutrons, protons and neutrons, and also protons and protons. This force is repulsive at distances less than 0.5 femtometers and attractive at distances larger than this. It has a maximum attraction at around 1 femtometer, and the attraction decreases from 1 to 3 femtometers, and it's considered about negligible at around 3 femtometers. Note, a femtometer is 10 to the minus 15 meters. Thus, in a small nucleus with a moderate number of protons, the repulsive electromagnetic forces and the repulsive strong nuclear forces are counteracted by the attractive strong nuclear forces, making the nucleus stable. However, in a large nucleus, the strong nuclear force becomes weaker relative to the force caused by the electromagnetic. So a greater proportion of neutrons is required to keep the nucleus together, because you'll need more attractive forces to balance out with the increased repulsive forces caused by having more protons. There are 4 main types of decay that AQA include in the specification. These are alpha decay, beta minus decay, beta plus decay, and gamma decay. Note that there are other decays which do exist. So the first one we'll look at is alpha decay. In alpha decay, an alpha particle splits off from the nucleus. An alpha particle contains 2 protons and 2 neutrons, also called a helium nucleus. Note that AQA loves to try and catch people's out. It is a helium nucleus, not a helium atom, because a helium atom would contain 2 additional electrons. However, in an alpha decay, only 2 protons and 2 neutrons are ejected from the nucleus. This is why we call it an alpha particle or a helium nucleus. The next one is beta minus decay. In this decay, a neutron in the nucleus is converted to a proton, an electron, and an anti-electron neutrino. The newly formed proton remains in the nucleus, and the anti-electron neutrino and the electron are ejected from the nucleus. We call a fast-moving electron a beta minus particle, hence beta minus decay. Like in all interactions, the charge is conserved in beta minus decay. Also, the lepton number is conserved. That wouldn't happen without the neutrino. We also have beta plus decay. In this decay, a proton in the nucleus becomes a neutron, a positron, and an electron neutrino. The newly formed neutron remains in the nucleus, and the electron neutrino and the positron are ejected from the nucleus. We call the antiparticle of an electron a positron. The mass and rest energy is the same for an electron and a positron, but all the other properties are the opposite. The charge is the opposite, lepton number opposite, for example. We will look at lepton numbers at a later date. The charge is also conserved in beta plus decay. Also, the lepton number is conserved. That wouldn't happen without the neutrino. Finally, we have gamma decay. If the nucleons are arranged in a suboptimal way, it is possible to rearrange them to reduce the energy level of the nucleus, making the nucleus more stable. So when the nucleons rearrange and the excess energy is released as a high energy photon, also called a gamma ray. Now, how is the existence of the neutrino predicted? So earlier we were talking about how the electron and anti-electron neutrinos form during decays, but we didn't always know they existed. The scientists calculated the difference in the energy levels of the nucleus before the decay and the total energy of the new nucleus and the beta particle after the decay. However, they found an inconsistency in these numbers, because according to their initial idea that only a beta particle was released, each beta decay should, in theory, release the same amount of energy, as it's the same amount of particles. However, the total energy change of the nucleus and the energy of the beta particle varied in recorded experiments. However, we know that energy must be conserved, as energy cannot be created or destroyed. So the rest of the energy must be contained in some other particle. This was the neutrino. In addition to conserving energy, the neutrino conserves the lepton number in a beta minus and a beta plus decay. So further experiments later proved that the neutrino did exist. Thank you for listening to this video. We hope you benefited from this physics lesson.